In this video, we're going to look at some other examples of calculating the equilibrium constant K sub C. In both of our previous examples, the starting concentration of the reactants were the same, but what will happen if the initial concentrations of our reactants are not equal? Consider the reaction, hydrogen plus iodine forming 2HI. We've actually seen this reaction before, but in the previous example, the initial concentrations of hydrogen and iodine were both the same. Whereas here we have hydrogen's initial concentration is 0.1 molar and iodine's initial concentration is 0.2 molar. We want to calculate the concentration of all species at equilibrium. So let's start by writing our ICE table. We have our hydrogen plus our iodine in equilibrium with 2HI. We're going to have initial, change, and equilibrium concentrations. Initially, H2 is 0.1 molar. I2 is 0.2 molar, and there's no product initially, so we can plug in 0 for HI. We can say let X equal the change in the hydrogen concentration, which is also the same as the change in the iodine concentration. So essentially hydrogen would be minus X, because when it reacts it'll go down by 1X. Iodine will be minus X, and our product HI will be plus 2X. Remember that we need to look at the coefficients in the balanced equation in order to determine the stoichiometry, or how it will change when it reacts. Our equilibrium line then for hydrogen will be 0.10 minus X, iodine will be 0.20 minus X, and HI will just be 0 plus 2X, which is 2X. We can now write our equilibrium expression. K sub C will equal HI squared over H2 concentration times I2 concentration. We can take our equilibrium line that we determined and plug those equilibrium concentrations into our expression. We also know our equilibrium constant, K sub C, is 57. So plugging in 57 for K sub C, that's equal to 2X squared over 0.10 minus X times 0.20 minus X. In a previous example, we were able to combine the bottom terms as a squared term because the initial concentrations were the same. But now that they're different, we're not able to do that. So we're going to actually have to use FOIL on the denominator, or first, outer, inner, last, in order to break it down further. So 57 is equal to, if we take 2x squared, that will become 4x squared. And when we multiply 0.1 by 0.2 for the first term, that will give us 0.02. And then for our outer term, we would have 0.1 times negative x. So that would be 0.10x, and it would be negative. Our inner terms would be negative x times 0.20, so that would be minus 0.20x. And our last terms are just negative x times negative x, so that will become plus x squared. We can combine the like terms in the denominator here, which is the negative 0.1x and the negative 0.2x. So that becomes 4x squared over 0.02 minus 0.03x plus x squared. So now we have an x term and we have an x squared term. We're going to end up having to use the quadratic equation to solve this. But in order to do that, we need to combine all like terms first. So we need to get our x squareds together. And in order to do that, we need to get that whole thing out of the denominator. And so we can multiply both sides of the equation by that whole term in the denominator. So moving that bottom over to the other side will give us 57 times 0.02 minus 0.30x plus x squared, and that will be equal to the numerator, which was 4x squared. We can distribute the 57 term through to everything here, and so that will give us 57 times 0.02, which is 1.14, 57 times negative 0.3x, which comes out to negative 17.1x. And then 57 times x squared is just plus 57x squared. That's all equal to 4x squared. And so in order to use the quadratic equation to solve this, we need to put it into what's called standard form. Standard form is ax squared plus bx plus c is equal to 0. And then we'll need to determine what our a term, our b term, and our c terms are. So in order to set this whole thing equal to 0, we just need to subtract 4x squared from the right hand side of the equation and move it over. So we'll be left with 1.14 minus 17.1x plus 57 minus 4 will be 53x squared, all equal to 0. And then 53 would represent our a, negative 17.1 would represent our b, and 1.14 would represent our c. Notice there's a negative in front of the 17.1b term, but in the original equation it's positive, so we have to include that negative sign with it. The quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac all over 2 times a. And so there's two roots with the quadratic equation. There's a positive root and there's a negative root. And we have to check both of them. Only one of the x's will be our correct answer. One of them will not make sense either according to our initial concentrations. So we have to take them one at a time and figure them out. So first let's start with the positive root. For our positive root, we'll have x equals negative b, so that's negative times negative 17.1 for our b term, and then we're putting a plus here because we're looking at the positive root. Square root of negative 17.1 squared, so b squared, minus 4 times a is 53, times c, 1.14, and that whole thing over 2 times a, which was 53. And when we calculate that x value for the positive root using the quadratic formula, we get x is equal to 0.229. And now remember, we assigned x to be the change in concentration of our hydrogen or our iodine. This x value is actually bigger than our H2 concentration, and it's bigger than our I2 concentration that we started with. We can't have a change in concentration that's larger than the initial concentrations that we started with. Otherwise, we'd end up with a negative concentration at the end, and that's not possible. So the x that we got from the positive root of the quadratic equation is no good. We can throw that term out. So now we're going to check the negative root. And we would have x equals negative times negative 17.1, so negative b. Then we're going to have a minus here. Square root of negative 17.1 squared minus 4 times 53 times c, which is 1.14, divided by 2 times a, which is 53. And checking our negative root, our x value should come out to being 0.0941. This x value makes sense. If x is the change in the initial concentrations of hydrogen and iodine, 0.1 could reduce by 0.09, 0.2 could reduce by 0.09. It's a value that's less than both of the initial concentrations. So in this case, this is going to be the x that we go with now to calculate our equilibrium concentrations of all species. So using the negative root in the quadratic formula, we got x equals 0.0941, and that's a molarity. That's the change in concentration of our reactants. So looking back at our ice table, at equilibrium, H2 concentration was equal to 0.100 minus x, which that'll be 0.100 minus 0.0941, and that comes out to being 0.0059 molar. I2 concentration was equal to the initial concentration, 0.2 molar minus X. So that equals 0.2 molar minus 0.0941. And our I2 concentration is 0.106 molar. And our product, the HI concentration, was 2 times X. So that'll be 2 times 0.0941, which comes out to 0.188 molar as the final concentration at equilibrium. There are some situations where you can avoid using the quadratic equation. If the value for K sub C or K sub P is very small, typically on the scale of 1 times 10 to the negative fourth or smaller, then we can make some simplifying assumptions to avoid using that quadratic formula. Essentially, we will end up being able to ignore any x's that are added or subtracted in our equilibrium expression. And this is because, according to significant figures, we wouldn't really be able to add or subtract them anyways, because the value that we would get for the change in the concentration of the reactants would be so small that we couldn't subtract it from the initial concentration. Remember, if you have a very small value for your K, C, or Kp, the magnitude of it is small. That means that you have a reactant favored equilibrium. And if it's reactant favored, the amount that the reactants react is going to end up being really small. So that will lead to X being a very small value. And X is our change in concentration. So let's imagine that we have some reactant, A, and we have the initial concentration, and we say it's 0.1 molar. Well, whenever we find out what X is going to be tiny. So maybe X ends up being 0.00001 molar as the change. In theory, we would need to end up subtracting our change in concentration from our initial concentration. And so we would take 0.001 molar and we would subtract 0.000001 molar. And now you might remember the rule of sig figs. We can only keep as many digits past the decimal as there are in the number with the least digits past the decimal. So in our first number, there is 3 digits past the decimal. And in our second one, we have 1, 2, 3, 4, 5, 6 digits past the decimal. So in reality, we didn't know what these numbers were right here, so we didn't ever assume they were 0. We couldn't really end up subtracting them from here. So when we did that subtraction, we would still end up with 0.001 molar as our final equilibrium concentration. And in reality, the initial concentration would end up equaling very close the equilibrium concentration of our product if this reaction was A going to B. So this assumption of ignoring any x's that are added or subtracted works really well when you have a very small value for your equilibrium constant. Let's try an example using this simplifying technique. We have the reaction 2H2O forming 2H2 plus O2. And notice our value for our equilibrium constant K sub C is 7.3 times 10 to the minus 18th. It's a very small number. So this is a very reactant favored equilibrium. That means that when the reaction occurs, it's going to stay on the side of the water. There won't be very much hydrogen and oxygen produced. Let's set up our ice table. We have our 2H2O2 in equilibrium with 2H2 plus O2. And then we have our change in our equilibrium. We were given our initial concentration of our reactant, so we can plug that in. 0.100 molar for the H2O. And initially we have no product, so we plug in 0 for hydrogen and 0 for oxygen. Using the coefficients of the balanced equation, we have a 2 out in front of the H2O, a 2 out in front of the H2, and a 1 out in front of the O2. So our change in our concentrations is water is going to go down by 2x, hydrogen is going to form by plus 2x, and oxygen is going to form by plus 1x. Our equilibrium concentration of the water will be 0.100 minus 2x. Our H2 will just be 0 plus 2x or 2x. and our oxygen will just end up being X. We can write our equilibrium expression next. K sub C will equal H2 squared times O2 all over concentration of H2O squared. So look what happens now when we take our equilibrium line and we plug those concentrations into our expression. K sub C is 7.3 times 10 to the negative 18th, and that's equal to H2, which is 2x, and then we would square that term, times O2, which is x, all over 0.100 minus 2x, and that whole thing would be squared. So this would be rather complicated to solve because in the numerator, we would end up with 4x squared times x, which would be 4x cubed. And 4x cubed, and then we would have an x squared term in the denominator. So we couldn't even just use the quadratic equation to solve this. We would need to use a formula for solving cubed roots as well. So to make this simpler, because we have such a very small value for k sub c, we can ignore any x's that are added or subtracted. Now, this value right here, 2x, that's subtracted from the initial concentration. Whatever x ends up being, it's the amount of oxygen that's formed and 2 times that amount of how much water reacts. It's going to be a very small value. And so we won't be able to subtract it using significant figures from our initial concentration of 0.1 molar very well anyways. So we can ignore this whole minus 2x term. We don't want to ignore the squared, we still want to square our value, but we can ignore the minus 2x. We never ignore any x's that are added or subtract or multiplied or divide, but we only ignore the ones that are added or subtracted. So now if we rewrite this fraction, on the top we're going to have 4x squared times x, which will become 4x cubed, over 0.100, and then we still have our squared there. And that's all equal to our k sub c, 7.3 times 10 to the minus 18th. So we get rid of this whole minus 2x term there. The 2 out front doesn't matter either. If it was minus just x or minus 3x, minus 2x, we're ignoring that because it's subtracted and it's small. And so then we can continue to simplify this and solve for x. And this should actually say 0.10 squared at the bottom there. So now we want to get that 0.1 squared out of the denominator. We can multiply both sides by that. And that gives us 4x cubed equals 7.3 times 10 to the negative 20th when we move that over. And we'll divide both sides of the equation by 4 here to move that over. And that'll give us x cubed. And x cubed comes out to being 1.83 times 10 to the negative 20th. Once we have x cubed, we can take the cubed root of both sides of the equation in order to solve for x. So if we take the cubed root of x cubed, that'll just give us x. And then if we take the cubed root of 1.83 times 10 to the negative 20th, we end up getting x equals 2.63 times 10 to the minus 7th. And so now to figure out our concentration of all species at equilibrium, our concentration of H2O was equal to 0.10 minus 2 times x. And essentially what we get is going to end up being very, very close to our initial concentration of 0.10 because 2 times x is still so small that we really can't subtract it. If we actually calculate what that really is, 0.10 minus 2 times 2.63 times 10 to the negative 7th, that comes out to being 9.99 times 10 to the minus 2, which is pretty much about 0.10, which was our initial concentration. So sometimes you'll see that they just write down the same initial concentration for the reactants when you have a really small value for the equilibrium constant. Our hydrogen at equilibrium was equal to 2x, and so that'll be 2 times 2.63 times 10 to the negative 7th molar. and that comes out to being 5.27 times 10 to the minus third as our concentration. And for O2, that concentration was equal to X. So that'll just be the 2.63 times 10 to the minus 7th molar that we solved for. So whenever we have a value that is about 10 to the negative fourth or smaller, you can save yourself some work by ignoring x's that are added or subtracted.